All right, let's talk about some carbonyl compounds. We'll firstly focus on ketones and aldehydes, but what is a carbonyl compound? Well, carbonyl compounds have CO double bonds. They have a double bond between a carbon and an oxygen atom. So they include aldehydes and ketones that we'll talk about in this video, but they also include things like carboxylic acids, esters, and amides. Now, both the carbon and the oxygen in a carbonyl group are sp2 hybridized. So both are trigonal planar. In the case of the carbon, it has two non-oxygen substituents and one oxygen substituent. So three sigma bonds and one pi bond. So it uses its p orbital to overlap with the p orbital of an oxygen atom next door. And so the oxygen atom has two lone pairs of electrons, and they're in sp2 hybridized orbitals as well. The simplest carbonyl compound is formaldehyde, and it's important to note that there's a charge distribution because oxygen is more electronegative than carbon. Oxygen is delta negative and carbon is delta positive, and because it's a double bond, that tends to get sort of enhanced, and so the polarization of a carbon-oxygen double bond is more important than the polarization of a carbon-oxygen single bond. So this should be a delta sign. So the delta positive of the carbon and delta negative of the oxygen. And that means the carbon is an electrophile. It's got a partial positive charge and it's seeking out negative charge to form a new bond with. So firstly, ketones have a carbonyl group that is in the middle of sort of a carbon chain, whereas an aldehyde is at the end of a chain where we have one bond to a hydrogen. So cinnamaldehyde, this benzaldehyde, which is called vanillin, citronelle, they're all aldehydes because they have a hydrogen here at the end of the chain attached to the carbon that is part of the carbonyl group. These ones in red are ketones because we have the carbonyl group in the middle of a hydrocarbon chain, so the carbon has two non-hydrogen substituents in each of these cases. So things like camphor, progesterone, and testosterone are all ketones. To name a ketone, we simply replace the -ane ending of a hydrocarbon with the ending -one, and we give a number to where that is in any situation where there could be more than one possibility. So propanone doesn't need a number because if the carbonyl group was anywhere else, it would be an aldehyde, so we'd name it differently. Whereas this compound here, the carbonyl group could be at the 2 position or it could be at the 3 position and so on. And so that must be numbered as a 2-one to tell you where the carbonyl group is. If it's in a ring system like this, then we don't need to use a number for the ketone because the numbering will always start at the ketone as 1 and then we'll move towards the first substituent. So there'll be 1, 2, 3 like that. So it's 3-methoxycyclohexanone. Aldehydes are similar. Instead of an -one ending, we give them an al ending, Al. And by definition, because the aldehyde has a hydrogen as one of the groups attached to the carbonyl group, and hydrogen is univalent, it doesn't make any more than one bond, then it is always going to be at the end of a chain. So we don't need to number aldehydes. So ethanal is the 2-carbon aldehyde, propanal is the 3-carbon aldehyde, butanal, pentanal, and so on. And then we have some special cases such as benzaldehyde, where we have the aldehyde attached to a benzene ring. We can also have conjugation. So if we have a double bond, a CC double bond of an alkene that is directly adjacent to a carbonyl group, we call that a conjugated system. And we can give Greek letters to the positions at which those carbons of the double bond are located. So next to the carbonyl group is the alpha position, one further along is beta, and so on down the chain. So it's only alpha beta, so it's alpha comma beta, unsaturated carbonyl compounds that we call conjugated. And the simplest one of these is actually acrylaldehyde, which is actually more commonly called acrolein. Acrolein is actually a pyrolysis product of things like tobacco, and is formed when you cook. If you've got oils that are smoking, then you'll be forming some acrolein, and it's quite nasty. It's quite a reactive chemical, and it's not good for your lungs and for your body. The properties of aldehydes and ketones are fairly straightforward. So we've got that polar carbonyl group, delta minus at oxygen, delta positive at carbon. And we can also think of this in terms of resonance contributors. So we can get the CO pi bond and move that pair of electrons onto the oxygen. So we're moving electrons towards the more electronegative atom. And so we have a resonance contributor that has a negative charge on oxygen and 3 lone pairs of electrons. And that resonance contributor has a positive charge on carbon, and that carbon has a vacant p orbital. And so this resonance contributor and this one contribute to the overall structure of the molecule. Now, the low molecular weight aldehydes, which are shown here, and the low molecular weight ketones are all soluble in water to some extent, and as you go to higher and higher chains, you have more lipophilic size to the molecule, and so the water solubility goes down as we go to larger molecules, and the boiling points go up as we go to larger molecules. There's no real sort of surprises to the trends there. Hydrogen bonding is possible with ketones and aldehydes, but it's not as important as alcohol. So we can only have hydrogen bonding between donors such as water or alcohols to the carbonyl oxygen itself in this format here. To prepare ketones, we can do this a number of ways. One way is to oxidize alcohols, and to get to a ketone, we must be oxidizing secondary alcohols. So secondary alcohols will lead to ketones. If we want to get to aldehydes, we're going to oxidize primary alcohols. If we get an aldehyde, we've done a sort of a partial oxidation, but we can oxidize further to get to carboxylic acids. Tertiary alcohols, because they have no hydrogens next to the alcohol, so we can't form additional carbon-oxygen bonds without losing R groups, tertiary alcohols are not oxidizable. So one of the most common ways to do this oxidation is with chromium-6 compounds. And chromium-6 compounds are notorious because they're carcinogenic. And if you've seen the movie Erin Brockovich, then this is Erin Brockovich, who was involved in uncovering a cover-up of chromium-6 compounds getting into a water supply in a small community in the US. So oxidation of a primary alcohol will initially give an aldehyde, and if it goes further, it will go to a carboxylic acid. Aldehydes and ketones, once we have them, can do a variety of reactions. They're particularly susceptible to nucleophilic attack. That delta positive at the carbon atom means that nucleophiles want to attack that carbon atom to form a new bond, and we're going to break the weak pi bond and push electrons onto the oxygen. So we'll get a negative charge in the oxygen, and then that oxygen atom could, for example, pick up a proton off a acid source of some type, such as the hydronium ion, and therefore we'll get an alcohol, in this case here. One of the most common nucleophiles that we use to get to new compounds from aldehydes and ketones are Grignard reagents, and they're named after an early 20th century chemist named Victor Grignard. And this is really covered in much more detail in sort of later year organic chemistry subjects. We can also go back the other way, so we can oxidize alcohols to get to ketones and aldehydes. We can also take aldehydes and ketones and reduce them back to alcohols. So aldehydes with hydrogen and a catalyst such as palladium will be reduced to primary alcohols, and ketones will be reduced under the same conditions to secondary alcohols. And remember your acronym, OILRIG. So oxidation is loss, reduction is gain of electrons. Another way to do reduction reactions that is actually much more common in many respects than using hydrogen and a catalyst is to use hydride ion. Or actually, hydride ion has problematic reactivity because it's very strongly basic as well as nucleophilic, we often or normally use reagents that react as if they're hydride. So we use sodium borohydride or we use lithium aluminium hydride. And what they do is they donate one of their hydrogen groups as if it was H-. So it gets donated to a carbonyl carbon, and we initially get intermediates. Don't worry about the structure of those too much, but then we treat them with water and often a bit of acid to speed up the degradation to give us alcohols and some side product borate salt. Okay, so that was a little overview about the structure and the function and the reactivity of ketones and aldehydes. Don't forget, important is the fact that the carbon is much less electronegative than the oxygen. So it's polarized delta positive at carbon, delta negative at the oxygen, and therefore that carbon wants to react with nucleophiles such as hydride or other nucleophiles such as Grignard reagents. Okay, thanks for watching.